Well, thanks for coming to the 5th anniversary of our humble meetup. It's been a long road. Yeah. Cheers to that. I'm glad that we're still going strong after so long. It's pretty impressive. We have a great community. I wanted to do a cheers with this Prosecco that we brought. But this is for all of the loyal members, old and new, that are coming to the user group and supporting us as a community, people who speak, people who help out. It's all very much appreciated. The group wouldn't be anything without the membership, right? So cheers to you guys. Awesome. So let's get into, let's get into the new library that I've been working on. So quickly, I just want to caveat this. I figured that I'd be able to polish it up more than I have been able to in the time between when I came up with the idea for this talk and now. So it's still a little bit rough around the edges because originally it was part of a big piece of software that we had and I factored it out. So API isn't necessarily nearly as important when something's just being called from one place in your code. And I've been working on trying to make it the names nicer and stuff, but it's still kind of a work in progress that way. Although the core functionality is all pretty solid. We've been using it for 3 years. So the whole idea with Fungible is we had this problem. So let me just give a little background information first. What we do at Bayard Rock is anti-money laundering. We essentially take in bank data and then we essentially match it against this big database of bad guys we have. And then for each pair, we have a probability that they're the same person and a risk score based on how risky that person is. Usually that's derived directly from our database using PageRank, something like PageRank, at least. But we work on site at a lot of banks, and often we run into weird data quality issues, all the time data quality issues. And over time, the settings file was just exploding with Booleans for each, every single field, like city, state, person, whatever, person name. There would be a Boolean for each individual operation that you could perform on that thing. It was getting out of hand, right? And it was very difficult to manage. So I came up with the idea of this library, which just named it Fungible a week ago. It's not, we didn't call it that. Essentially, originally it was called record cloning because I was going to clone and then mutate, but then I decided I could do it a better way. Essentially by injecting the changes as it's being cloned. And it's been awesome. Essentially now it's you have one function that operates on a string remove space characters. And you can just say, apply the remove space characters function to this part of the tree. And that will just, instead of having a Boolean for each thing, now it's a little kind of scripting thing where you can say, do this here. And you can even extend it further. I'll talk about that more. The basic idea is pretty simple. We have these basic combinators in functional programming like maps and filters and stuff. And you just apply those at certain places in the tree. You'll see it'll be more obvious how it goes on. The side benefit is adding these little Boolean features all over the place was extremely boring. And we have to ship out, largely it was a build process thing where you have to ship out these changes over and over. And instead now, I got to play with quotations and expressions and do some really cool work that actually was quite a lot of fun and required some thinking. So this is sort of the structure we have. It's kind of a very simplified version just for thought purposes, but we have a pair of records, a customer record and a list record or a provider record. There's lots of different names. And then we have all these different kinds of functions, we want to be able to strip out the accented characters, essentially replacing O with an umlaut with a normal O to facilitate matching against normal English. You want to be able to ask questions is the country local, or do you want to replace certain substrings, or there's even strip out weird ASCII character or Unicode characters that make it in somewhere. There's a million different examples, and you just want to be able to combine them together and apply it to that part of the tree. This is just sort of a motivating example. So there's two main things that this is based on. So first we're just going to talk about the core, which is actually used by other things. So it's not as user-friendly, but it's really important to understand this because it's also the cool part, and it shows you how it all works. Essentially, you have a path, which is a string list of member names that goes into the tree. And then you have a field updater list, which is all of the things that you're going to do at that spot in the tree in that order. It's pretty simple. So it's just a map from these paths to the actual actions that are going to be performed in that tree. Because the string list, because it's a map and keys have to be unique, you don't have to worry about something being said more than once in there. It like has nice properties for that. So yeah, that's pretty much what it comes down to, is you take these pairs of paths and stuff and you just pass them in and then it does all the magic. So for most of this talk, we'll be using a structure like this. We have a bunch of entity records. Because AML is weird, we have things like people with multiple dates of birth and multiple names, badly formatted dates of birth. So we use our own date class, which is essentially just like, numbers that we can validate independently because the .NET date time doesn't really support a 0 per day. But we might not have a day for someone's birthday. In fact, sometimes we have a range of values, to be honest. Because they can kind of like triangulate, like you can say it's within this time, based on the media that's been published about some person. And also names, there's like aliases and various spellings and this.
I mean, is it really reducing down to that few number of people as responsible for the greatest amount of fraud?
Well, it's not fraud, it's anti-money laundering, which is different. Okay. So like we're looking for essentially two kinds of people. Politically exposed people, which are like ambassadors and presidents, ministers of finance, whatever, people that are in position of power. So the UN says you have to monitor for them, essentially. All they do is like watch their transactions more closely. And then there's the legitimate bad guys like Victor Boot, who is like a notorious international arms dealer, and various other people, Al-Qaeda members, whatever, that those get reported directly to the government, of course. But so here we can see like what the sort of paths look like in their raw form. So for the names field, so the entity is implicit because that's the root object. You don't talk about it at all. It's just, we talk about the members it has. So to access the names, it's just names. And this is a little bit weird, but for this locations.state path, because if you notice, it's backwards, it's state and then locations. But that's because as we're processing, we're appending each level to the head. So like it ends up backwards and it just makes it easy to match in the map based on that. This is not really exposed to users. I mean, it is exposed, but we don't use it that way. So it's kind of just convenient and requires less computation to have it in that form. And then we also have the type. So, string option, string array, whatever, and we can look transparently through those levels of types. Now, obviously that our software is processing like some large number of these, sometimes millions of these pairs. So what we want to be able to do is generate these transforms, compile them, and then cheaply apply them to all of these records. And that's part of the whole game, is like to make it really cheap to do this. It reduced the number of allocations. And so instead of like, what you might know about lenses, where F# with lenses, you have to allocate for each and every lens every time you will make a change. In this case, because it's doing the whole shebang at once, it's just as many allocations as needed to replace what is necessary.
Question?
Sure.
I see a lot of strings there. Are those all literal strings, or do you have patterns? Like regular expressions or more fancy patterns in there?
Well, we do use those at other places in the software, but here, this is just the representation of a person.
No, I mean, for the entities, you seem to have literal strings, but when you're doing you want to identify a path in a tree, do you ever have options like, instead of an exact match, do you have like fuzzy matching?
Oh yeah, there's a whole lot of fuzzy matching logic. So this talk isn't really about, like, this is just one little tiny piece of this giant thing. It's like something like 30 F# project files in a solution, with like each with at least 5 to 10 F# code files that are multiple pages long. So it's a pretty big piece of software. I mean, it's not like, I don't know, AT&T scale or whatever, but it's sizable. It's a sizable code base. This is just one little part of it that I decided to open source because I thought it might be useful to other people. We've slowly been trying to take out parts that are useful and give them back to the community. Like, as long as it's not our secret sauce, what does it matter? It could just help other people, right? We can talk about the different kinds of things you might want to do to data and how they relate to F# functions. Although it's a little bit weird to be fair. And I'll get into that in a second. So, the basic idea, like oftentimes you want to strip out the parts of the contents of strings, or you want to make something all uppercase for matching, or whatever else. That's just a straightforward map. One thing goes in, one thing goes out. The vast majority of the time, this framework is used with maps, because we're doing like, oh, we want to strip out these weird Unicode characters or whatever, or convert like double spaces into single spaces or whichever. But filtering is also useful because, for example, in bank data, oftentimes they use certain dates as defaults. So like there'll be a date that looks like, for like a date of birth, that looks like a legitimate date of birth, but it actually is like, you do the data profiling step and you're like, wow, like half the database was born on this day, which is usually like 1/1/1979 or something like that. So being able to filter those out in this step is very handy. And there's lots of other cases where you might want to filter out weird tokens or other things. Collect isn't used as often, so what collect does is essentially it takes one thing and turns it into multiple things. One example of this would be like string.split, where you're taking one string and turning it into a bunch of strings. This is used somewhat not that often, but it can be nice for, like for example, sometimes we have situations where it's like two names in one field, or two dates of birth in one field. Bank data tends to be really crummy, which is why this is so flexible, because I don't want to get a phone call essentially telling me we need a new version of our software because we have this new customer and there's something wrong with their data that we can't fix with what's already there. Default is interesting because oftentimes you want default values. Like, if you're working with a US bank and there's no country or citizenship, you might just want to stick USA in there because it makes the rest of the algorithm run smoother, have that assumption. And it's better not have that other part of the system to have to know about that as much. Sometimes that could be useful for saying like, well, the probability is slightly less because it's an injected value that didn't actually come from the data, but it really is not really that, like the probability change is not significant because the vast majority of people that have like TD bank accounts that live in New York City are from the United States or whatever, or maybe that's a bad example, but like, various different banks in their places. Most of the people live in the US. And add is also very interesting because the reason that you'd want to use add isn't necessarily because you want to add something like a country value, but it's really useful when you have data somewhere else in the tree structure and you want to add it to a different place. So you have essentially in scope with the more advanced version of this, the entire tree structure as well as the current value you're operating on. Most of the time you just want the current value, but sometimes like if you have additional fields in a map and you want to take one of those and like, oh, this was actually a name field that we missed in a different part of the process, we can take that and stick it using add into another field. And then eventually I had to add a function, which essentially is sort of like a map, but for just singular values or whatever it is. It gives you like the actual thing as opposed to trying to be smart about it because it's just, in some cases you just need that. You need just like no shenanigans. I just want a straightforward function from the one type to itself to replace some value. I'll give you an example of that later.
If you take it in A to A rather than A to B or something?
Well, it's because the type structure of the tree is fixed, right? Like the type tree is, if we go back here, it looks like this. So like, we can't take that address and turn it into a some other type because it's just, we have this structure and we're turning it into this structure over here. But yeah, you're right, like these are normally A to B and such, it's just that in this case it's constrained.
So the merge, you'd have to create something that already closed the data that you need to add, right? Or the way to get the data you need to add?
So yeah, the way we do it is essentially we pass in two values instead of one to the function that's doing the operation. One of them is the entire tree, and the other one is the value you're currently operating on. Mostly for convenience, because you could figure out where you want the tree. In fact, you could probably do this whole thing with just a function on the tree if you could replace certain elements a certain way, but it gets really messy.
Sure.
And this keeps it very simple in most cases, but gives you like that escape hatch when you need it.
So it's not just a unit, it's the tree. is coming in somehow also.
Yeah, this is a little bit of a lie. Because
Okay,
what I'm
gotcha.
talking about here is like
Fine.
the structure, just the general structure, trying to map it back to F sharp. For most of this talk, it will be the case that it's A to A or A to bool or whatever. But there is like the extension using the barb language that I'll talk about later allows you to pass in the entire tree. So not all of the things work on, not all of the operations work on all of the data types, because some of them don't make sense. Like trying to add something to an option, it has a failure state, which I don't like, right? Like if you add something to an option type can either be none or some value, right? If you try to add a value to something that is a sum, already a sum, it'll explode because there's no room. It's a container that holds only one thing. So instead, you use default in that case if you just want it to be for none. And it makes it a lot less likely to have problems, essentially. And it makes the intent, I think, clearer. There are a few weird cases, like collect on maps. I didn't implement this because it's not straightforward to me how you might want to do that. Because for any new member of a map, you need a new key and a new value, right? And if you're mapping over keys and values, you need a way to transform that back. So I decided that it wasn't really worth doing for now. This is all open source though. We take contributions if anyone wants to work on. Union types are also kind of an edge case where they're not, like they work, but you can't really do much to them. Mostly because we don't really use union types as part of our record structure, so I didn't want to put a lot of work into that. And not a lot of these functions would really operate on a union type as they are. I think it needs to be rethought to some degree. So just in case you're not that familiar with F sharp, a union type is a type that can be one of several other types. And each of those have names. The way it works right now is like you can map over the union type contents. So like if something is in a union type, like there's an integer inside of the union type or something, you can change that. But what you can't do is swap in a new type for that union type. Also, if a tree path goes through a union type, and like because the branch is different and the thing isn't there, it just won't do the operation because they'll get that point and there's nothing to do. So yeah, this was very interesting to work on to some degree because of it's interesting to think about what operations make sense on different data structures. And a map is just a dictionary or a hash table, essentially. It's an immutable version of that. So we have some settings, which I just want to go over really quickly. So originally the idea was that I was going to actually just copy the whole thing and then make it all CLI mutable, which lets it be mutable from C# or whatever, and then make changes directly. So the original code structure supported that. I didn't want to get rid of it because it could still be useful for someone. So, but it's off by default. So essentially it does as little work as possible by only cloning the things that have dependencies down that need changing, instead of replicating the entire structure, which is more expensive. But you can turn that on and then it'll replicate the entire structure. The other Boolean flag is mostly for the failure state. I don't want it to explode when one of my users does something stupid. I'd rather have just ignore it most of the time. So we just have that fail on unsupported type false, so it avoids certain problems. All right, let's get into some code examples. This is just a little script I've been working on as I'm working this talk, I'm working on the documentation for this thing. So this actually is from the tutorials project, but it's not like, I didn't make it as nice as I would when I want to publish it. So essentially, this is just some standard F# X script, like FSX script. F# allows you to have either compiled or scripts. You can do it either way. So there's actually this library. It's sort of not really about this at all, but essentially there's something called F# formatting, which takes markdown annotated scripts and turns them into nice web pages with the code and the types and everything. You can mouse over types and see them, just like you can do in Visual Studio and get information. So that's super nice, and I've been working with that. So there's a few different libraries here. Barb is the little programming language that we'll be using later on, and there's an extension. There's also just Fungible, so you don't have to take this dependency on Barb if you just want to use this without that. This is opening some namespaces. So now the first thing we're going to do is define a structure that we're going to play with. Here we have 3 types. These are F# record types, where these are members of those types, and then the type of those members, essentially separated by a colon. So like a date has a day, month, and year. Address has all these string options. This is very similar to the slide I showed not too long ago. You have multiple names, multiple date of births, multiple citizenships, and then this thing called fields, which is actually something we really have in our real database, or our real software, which is just like anything we can't find a place for in terms of our structuring code, we shove in there in case we need it. And it comes in really handy for things like Swift messages or whatever else, when there's like, you might want to access that data for some machine learning feature, but you don't necessarily have it. So we'll just load those up. I'm just highlighting it and hitting Alt-Enter to send them down here to the REPL. When we hit Alt-Enter, it executes it and then tells you what the type looks like for that code. Then finally, we'll make a test person, which is me, although I changed some of the information to hide my identity from internet hackers. And down here, you can see the structure. I only have one, even though they're all arrays, I only have one value to make this easier. And also, this is kind of a side thing, but in option types are kind of optimized away to null when the compiler just kind of gets rid of them for reference types. So they're not, it makes things more efficient. Option types can be either none or some value, like I explained before. That's why you see here, when you have a city, you're essentially defining this address, and you're saying the address has no value, but the city is New York, which is some value. Making this explicit removes a lot of kinds of null case errors from your code. So first thing we're going to do is we're going to define a function to apply. And then we're going to wrap it, and this is an F-sharp quotation. The double @ symbol means an untyped quotation, because I found that it was just impossible to do this with the typed quotations, making everything knit together without having them be treated as objects in the first place, and then what's the point? If you're going to go untyped, you might as well go all the way. It still will, when you try to compile these things after they're all jammed together, if the types don't match up, it will still give you an error. This just kind of prolongs that and makes it a little easier to work with them in the meantime. So the way this works is in F-sharp too, you can define things inside of other things arbitrarily. Like let is sort of like var. You're saying, we're going to make this expression. So the first thing we're going to do inside this nested scope is define the function, and then we're going to wrap it in the untyped quotation, and then we're going to stick it in a thing that lets us know that it's a map. And then this is returned down to here. So if you look at the type here, you can say, I can't make that bigger, I don't think, but it says it's a field action, essentially, which is one like map filter or whatever. So we're just going to run that in the REPL. And so next, what we have to do is essentially define some path, and then where we're going to apply that function, essentially. Then we're going to turn it into a map. So what we're saying here is we have this is a path. It's the locations and then the city field. Like we talked about before, it's backwards. Then we have a list of different operations to perform at that spot, and then we just turn that into a nice map. So we can just take that function map, and now we need to make the transform. So we take this generate record transform function, we parameterize it with the type of the thing we're dealing with, which is the root object. There's also those settings we talked about before, we're just using the default settings. And then we're passing in the function map. Now this is a partial application, if you might have noticed. Essentially, this function takes this all the way up through the transforms, which are like the things in the function map, essentially. And so what I'm doing here, just to make the code nicer, is partially applying the settings in the function map. And then, oh, I'm sorry, it's the other way around with this case. I was a little bit mistaken. We're actually building the real transform here. But the actual result, this actually does work, but it returns a function from person to person, which is essentially that tree of operations applied. And then we just take our test persons and we map over them with the transform. We'll throw the transform in here, it's a person-to-person function, and then we'll just run it. And we can see here, because we operated on city locations and we made things uppercase, this is now New York, it's all uppercase. While previously it was standard, like capital So pretty simple, right? Not too bad. So just to show that it works in multiple locations, this time we're going to do it on the address field. Now in this case, actually there's more to it than that. We know the address field is null, and this does not give us an error, it should just be transparent when there's no value there. So the only difference with this one is that we're going to apply the transform to something where the transform is not valid, just because in this particular case, that option type is missing. So we're going to do it, and you can see like nothing happened, the address is still null, and everything's okay. Okay. So we can also apply these functions all over the place. So this is more like something you'd see in the product, or at least the resulting intermediate map. There's something that builds this nicely, and I'll get to that. But here, we want to apply that to all these places. So this is just demonstrating that we can have a whole bunch of different paths, with the same or different functions, make it a map, and then apply that. So we're just going to take our map. Now we're going to take that and make it all into one nice transform. So essentially, this is still a person-to-person function. It's just going to do all these things at once. And then we can apply that, and we can see like everything is uppercase now. Pretty simple, right? And we can also apply multiple transformations to the same field, which I talked about a minute there. So we have this one, it's just like it's going to remove uppercase vowels. And it's very similar to before. We have our function here, this is the actual function, and then we're just wrapping that and returning it into this structure here. I know F# is a little bit different than like most imperative languages in that you can just scope things. So essentially, like you can have the contents of this and then reference it here, and just essentially, you don't use the return type, the keyword return in F#. You just have it be the last thing laying around, and that gets returned back up into here, which is the field action. I know it looks a little bit funny at first, but this is super convenient. And one of the nice things about this with F# is that you can really scope things narrowly. So it means that your namespace, your variable namespace, so your programming doesn't get full of stuff. Essentially, because you can just put things in the scope where they're necessary, it becomes a lot easier to work in this code, because now when you go back to it, the things that are in scope are just relevant to what you're doing, instead of like a standard imperative program where there's lots of variables and most of them have nothing to do with what you're working on.
So what is the advantage of using a quotation there?
So the reason we're using a quotation is essentially this whole thing is based on quotations. Or what a quotation is essentially, it's a way to take F# code and turn it into an expression. And these expressions are what all this is built out of. I'll show you the code for that later. It's going to be like the last thing, because I want to get through like all of the parts first. But the whole idea is that we have to knit this into the tree of expressions essentially that are copying this data structure, and so it needs to be an expression. And we also want to wrap it in terms of the kind of thing it is, because it needs to be able to know like where it's applicable.
So you essentially use, it's like a list quote.
Like a what?
Like quote and list. You take
Yeah.
the expression, S expression.
It even gets its name from that, the list quotes, quotations. And essentially F# supports these, and they're kind of an advanced feature, but this is probably the easiest way to introduce to them. You also use them if you're making type providers quite often, because you use the quotations to be able to like generate members and whatever else, the contents of what happens when you call those members. I mean, I could have made it so that essentially I do the expression routing later, but it actually just makes the whole thing way simpler to not have to do that transform. Okay, so in this case, where was I? Oh yes, so we're applying two functions this time. The first one is going to make everything uppercase, and then the second one is going to remove all of the uppercase vowels. So if this happened in the reverse order, then you wouldn't see any of the vowels removed, because they would still, or except for the, I guess, no, like none of these words begin with vowels. So we're just going to apply this to the function. We have our two functions there in the map, We have our transform with a function map. We have a person-to-person function now, and we just apply that. And you see here, it's all the vowels been removed from New York down here. And this is just an example of what happens if you apply them in reverse order. It's exactly the same, except now you're going to see that none of the vowels are removed because we did the uppercase matching first. And I think this is really important that it has these sort of invariants so that you can reason about what happens in terms of when your users, like you're like, well, it's not working. Well, you know, did you reorder them properly? As opposed to having kind of willy-nilly. Okay, so that's it for now for that. Let's go back. So yeah, this is only like, so what we just covered is just the core part that does the work. Now there's a whole, or actually 2 additional layers that are there to make it easy to use and to make it work with our settings file and stuff like that. So I'm going to be going into that. The first is just using this with existing F-sharp functions and libraries that you write, and you can reference these directly. And the second is being able to write custom barb functions. Barb is a dynamic programming language that I wrote for essentially originally writing machine learning features. It supports like nice little set operators and stuff, so that it's really, the code compression with is really great. And it also has a very forgiving parser, so that like if a user forgets to put in like close their scope or whatever, it can try to work anyway. And you know, it'll automatically convert things like integers to a string if you want. Like, so when a user like is comparing something and they're on their web browser and they cut and paste this in and they don't put quotes around it or whatever, it'll still work. So Barb was sort of designed for that. And I'll get more into that later. Yeah, like I was saying though, this is not user-friendly. Like having the reverse strings, constructing it by hand, I don't think most people would want to deal with that. Like there's no point, right? So the next layer is the static reflection layer. So here's sort of an example of how it looks. I hope this isn't too small. This is actually a cutout from our settings file where we have fields. This is JSON. We have operations on those fields like strip accents, which takes no parameters. And then we also have parameters that they can take. So that, you know, for example, if we want to remove certain characters from a string, we can just list them here. There was sort of a compromise that was made to make it easy to integrate with the JSON libraries and stuff, where we just say, okay, these are always going to be strings, and we'll do the conversion as we build the tree for those parameters, just to make it easy. Although it would be nice if we could actually have the right types in here. That would be more work, and yeah, we needed it ASAP. So here's an example of one of these cleaning functions that comes from our internal library. We annotate it up so that it looks nice in our user interface. First thing we do is we tell everyone it's a map. Now, we might be able to figure this out in some cases from the type, but like the difference between a default and an add, they have the same type, right? So you really need some sort of label to let it know that it's a mapper or an adder or whatever. And then we have these descriptions on the parameters so that when we show this in the user interface, which I'll show in a minute, the user gets these nice feedback about what they're supposed to do. And then, you know, this is just code. Essentially, all it's doing is converting certain characters to spaces using a string builder, so it's somewhat efficient. It works pretty well, and we use this actually all the time for certain characters, like dashes or whatever. Here's another example. This one just is to show that it's not only about strings. And also, this is what the user interface helper looks like. It's sort of, we modeled it after the Excel like function explorer. So this drop down shows you all of the different functions that are available in scope, and then it tells you what the parameters are, and then gives you the description of how to use it. Actually, I'm moving my mouse around on my screen like you can see it, but yeah, like this stuff. So it makes it really nice for a non-technical user to be able to actually use this thing and kind of get a feel, in sort of the same way that Excel is very friendly to non-users. Because a lot of the people that use the software that I make are not programmers, even though there's like a bunch of scripting functionality and all this fancy dynamicness. The people that are doing the actual finding the bad guys, are not programmers. Maybe they have a little bit of, maybe they can do like basic SQL, and that's about it. So yeah, it's heavily optimized towards that kind of person. Also interesting is that there is an internal, so there are some things that I would like to make better about this for user interface from a library perspective. Like, because as right now, the different types that are converted, like date, which is our own internal date format, are not, there's no extension for that built into the Fungible yet. So it's just they're kind of hard-coded in there with wrappers. And it would be nice to be able to like make it arbitrarily extensible in that way. I think it's actually probably not that hard, but I've been kind of just rushing to make it not terrible. when I like showed it to you guys, you weren't like, oh man, I can't believe you made this crap. So yeah. So the basic definition of a static transform is just three things, as we saw earlier in the JSON. And it's CLI mutable because we're using like these property grids and stuff. So what CLI mutable means, it's an F-sharp annotation, and it says if you're not in F-sharp, you can mutate this. So the idea is that once we have it, things are pretty safe, and it also makes it serialization nicer in a lot of cases. A lot of serialization doesn't really work that well with things that are immutable. Yeah, so in any case, we have our path, our function name, and our function arguments. And if you go back here, you'll see that actually our paths are much nicer now. They're not like that crazy backwards list. Oh, where am I? Nope. Yes, it's just like you would expect if you were like calling it in .NET. It's like cust.names or cust.locations.city. So it's a kind of just a nice path into it that a normal user can understand. And that gets converted and then reversed when you're using the library. We also have it print nicely. And also these things show up sometimes on our user interface. So we use the description attributes like all over the place so that we can reflect those out and show the user like definitions of things. And then we have these XML comments so that it's unfortunate that you can't like kind of do them both at once. There's like no way to get double bang for your buck with that in .NET, but it would be really nice if there was, because I just pretty much have everything replicated. So this layer does a lot of stuff. As we talked about, it converts the paths to the internal backwards format. It does these type parameter, or not type parameter, function parameter conversions from the JSON so that we can just have strings. It looks up things essentially in terms of like names that are paths and turns them into method infos, or not names that are paths, names of functions, and turns those into method infos. And it also knits it all together in the end and makes it nice so that it's understandable. It also does a little bit of funny business in terms of wrapping types for conversions to make it nice, but I'm not really going to go into that until later. You can think about this at a high level, and there are some details that are kind of funny that come down to weird things about .NET and F# in general, but most of them are not problems here. So let's look at some code samples. So I call this static reflection after much thinking, but like I still don't really have a good name for what it is. Essentially, it's just, I call it that because it reflects over static F# functions that are not dynamic, they don't change, they don't come, they're in the assembly. So I think it's kind of reasonable, but it doesn't have that great of a ring to it. So how this works. Essentially what we do is we make a module of our functions that we're going to be accessing with this. Here we're just opening some new namespaces. I actually have to run this whole thing at once. Now this is an F# trick, because it actually is pretty hard to get the type of a module. It's kind of annoying in F#. So instead, what we do is we put this marker interface in here, and then we just get the type of that marker and get the declaring type, and make this just a static member of this module so that it's easy to get the type of the module out from it. This is a trick that you see fairly often, and it works quite well. It's a little bit silly, but it would be nice if we had like C# name of. That's a feature that's new in C# 6, I guess, and I'd really like to have that. Then we just define our function, essentially, and we annotate it up nicely. I didn't put the description attributes on here just because it takes some space. There's no real reason. So we're going to define this entire module all at once. Down here, we have a module. It's got the marker type, and the remove characters function. So to use this, we maybe settings is the best name. But anyway, this is the path, like you normally be separated by dots. We're calling the remove characters function, and in this case, we're just removing the capital R's and lowercase r's. I know these are kind of contrived, but I didn't want to make giant data set for this, and I thought it'd be hard. This is just to show what it can do in terms of the functionality. So when you're using this, the first thing that you have to do is generate a property map for this type. And this is actually really necessary for the entire REST. I thought about trying to do this internally and caching it. It's kind of expensive. So I wanted to make sure that, for now, it's part of the public standard API, because it actually is useful too. It gives you those paths, and then for the entire tree. It generates all of the paths, and it also gives you the type at that spot. So that actually is pretty useful for our user interface stuff, in terms of representing this. Then we just take to generate this, we have a special function now called generate transform. It comes from this. It only works on this stuff. So we have to tell it the module type, where to look for these stringly functions. We have to give it the property map so it knows if things are valid or not, and what the type of the thing is. And then essentially, essentially we just make this generator, which is just partially applied functions. It actually can take the whole thing if we had this not in an array, but you wouldn't normally use it that way. So we're partially applying that, calling it generator, so it's a function now from transform definition to transform, instead of a function from type, map, the property map, the basic transform, and then finally get a transform. This is just to make it nicer. And this is sort of how partial application F# can just be used for cleaning up your code and making it look nice. Oh, we need all this. So you can see here, it doesn't show the whole thing, but it shows you the locations.city is an option type of string, and this is listed out for the whole thing. And then we make our transform definition to transform, and then we make the transform. So essentially all we did here is now we've got a transform array, which only has one transform in it. And that transform, remove all of the R's from the name. So we take that. Now what we need to do is take all of our transforms and compile them into a tree, into this thing that generates all of the changes and copy stuff. So we're saying, essentially, this is kind of an oddity that it takes two types. Essentially, it takes a U, a T, and then returns a T. The U is a context type that you can use to give extra information or extra stuff in scope to the user. In this case, we're not using it all, so we're just going to stick person in there. It's not even being used. And we pass in our transforms, and what did I do? Oh, I didn't run this whole thing. There we go. Okay, we got our transform, our names. And actually, it's kind of cool because you can see the actual, this is the contents of the expression tree. It's straightforward. You can see it in the debugger. So it's just a call. It's a lambda with a call to remove characters with these values being coerced. So we'll just compile that. Now we've got a function from person to person, and one of those is a U, the other is the T, and then the result is the T. We're just going to pass in the same thing twice because it just does not matter here. And what we get back is Rick Minerich down here, because we moved all the R's. Okay, so that shows you kind of how this works. And so in practice, essentially what you would do is you would deserialize all of these from your settings file. Then you would pass them into the generator, create the transforms, essentially, and then compile all those into your tree, and then you use that. And then you pay this one-time compilation cost. And then if you've seen the benchmarks, expression tree stuff, once it's compiled, it's super fast. It's faster than reflection in most cases, so it's a really big win. Okay, let's go back to this. So yeah, Barb is originally a language that I wrote because there were no good options on .NET for just a quick little scripting language over data for filtering. You're in a user interface, you just want to see all the names that contain Rick or something, or all of the records that have a certain date of birth, or all of the records where the country is in the set of countries. This is a very common thing with the kind of work we do. Because you want to actually, when you have machine learning features and stuff, be able to check out different examples of how things worked out in practice. And so you can tune your algorithms and come up with new ideas and all kinds of stuff. And we also use it for the actual features themselves. So a user can take the string, put it in the little bar at the top of our application, and see exactly what records this will return true on. Those are the ones that the feature will affect, essentially. And so it's actually quite handy that way. It's got a REPL, although the REPL keeps no state because it's a stateless language. So it's not super useful for programming with the REPL. It's more just to play with and try out. And this is just a little picture of our app as of like 5 versions ago or something. It's all on GitHub if you want to check it out. I'm pretty proud of that work. This is how it would look inside of Safe Alert Manager, which is I'm going to take all this WinForm stuff and move it out into Fungible, like as a new library, so that you get all that stuff that we worked on for free. But as of right now, it's just the stuff that does the action-y stuff, the stuff that actually makes the transforms and applies them, does the reflection. It's harder to separate out the WinForm stuff. As you might have ever experienced, trying to refactor WinForms is not fun times. So yeah, we just have like a little window, and we say a predicate. This is actually the has intersection operator, and this is the kind of code that you would use. We just give a little reference of the structure over on the right-hand side as well, so that the user knows the names of all the things, because they need to supply a path. So this is what a barb transform looks like. It similarly has a path, just like the static reflection transforms. But what's different with barb is because it's dynamic language, there's no annotation. You need to tell it what kind of function it is. Is it a filter? Is it a map? Is it an adding function? Whatever else. And then there's actually the string, which is the function, the actual the text of the function that you're going to be compiling. So overall, this is pretty simple. It's just like the other one. We can deserialize it right from the file and just pass it on in. It's quite convenient. Things are a little bit more complicated with barb, though, because with barb, you want to be able to do a whole lot more, as opposed to just having a library of functions that you want to apply to values. Instead, oftentimes I'm called upon to solve some sort of semi-hard problem that's affecting the data, and this is sort of a shortcut. Like it's an out, essentially. I can write some pretty complicated barb, email it to the person. They sometimes have to type it in, which is the worst part because they always mess it up. Mostly the hard thing about barb is that there's no looping at all. It just it has recursion, but no looping. So if I want, I can do all the same things with loops, but it's not very nice. And that's only there so that I can have this emergency backdoor. Most of the time, this stuff isn't necessary. And usually, if I have to do that, I'll be adding a new feature to SAM in a future release that solves that problem better, but it's nice to have that. But anyway, inside of barb, what we have is 2 things. We have the value and the scope. The scope is the entire tree, and the value is the current thing we're looking at. It wraps different types. The most important one is maps, because unfortunately in F#, to make a map from a sequence takes tuples. To turn a map, like you take a map and turn it into a sequence, you get key value pairs, which is terrible asymmetry. Like it makes it so that it's just very difficult to deal with. So what I do is wrap it so that you always are dealing with key value pairs. They're also just nicer to use from barb than the tuples because it doesn't really have tuple decomposition. Although I'd like it to someday, maybe. That'd be a nice thing to have. The nice thing is that the result of what you generate from this is just a transform. Just like the static reflection transform, it's exactly the same in terms of like the type. And so you can just combine them together however you want. You can even interleave them if you want. There's nothing holding you back. So let's take a look at Fungible barb. This is actually like from barb because we're going to be using barb, so we need to open up the namespace. And this is just a bunch of extensions that make it nicer to use. So barb has its own settings for various things, like for example, barb by default assumes everything is immutable and no function calls that it make will mutate anything ever. This allows it to be very efficient because I can optimize away a lot of stuff ahead of time if I know that it's not going to change any world state, right? But for some people that might be a problem, so I added an option. It just does a ton of work. Essentially, it doesn't optimize anything at all ever. So I don't know if it's even that useful. So for an example, we have our names. We just map and we're going to make them lowercase. It's just a normal function. It looks kind of like .NET value.toLower. This is the name string because we have names. And if we actually typed in scope, it would be the whole scope of the tree. So we're just going to map over those names. We need to make our property map just like before. Now instead, we just generate barb transform instead of generate transform. It's a very similar structure. The only difference is it takes the barb transform definition instead of a transform definition. I want it to be very symmetric, so it's like easy to work with, right? And then we take our barb definitions and we just map over them with the generator, and we get a bunch of transforms. So I need to do all these at once. So just the same, we have our barb transforms, and we just compile transforms. And voila, right? We have our person-to-person-to-person function, and as you can see here, my name is now all lowercase because we called .to lower. I don't plan on going like into depth. I've given talks before on barb, they're online, if you're interested in the language. There's also a fair amount of documentation. I would like there to be more, but. So here we're just going to show that we can combine these things. So if we just take this array of barb transformations and append onto it the static transformations, now we've got two transformations. So, we've got this is actually kind of cool because you can see the internals. This is the barb transformation. It's got this application to some function, and it has to make the value container and wrap it. That's actually kind of cool that you can see all that. And then this is just the standard static reflection transform. So we're just going to compile those. We make another person-to-person-to-person function, except this time it has both of those in there. And if you notice, they're both applied to name. So it'll be a little bit interesting how that works out. So yeah, because we are to lowering, before we're doing the remove r's, it just actually doesn't matter because I'm doing the uppercase and lowercase r's. So that doesn't matter really that much, but it's still interesting. I think, and I think it works out nicely that you can just use them interchangeably. So the way we do this with our settings file is we have like two sections. We call them basic cleaners and advanced cleaners. And mostly I say, if you don't know how to program, just don't touch the advanced cleaners. Because they're also, to be fair, it's like with barb. Barb was not originally designed for this kind of data manipulation. I've been slowly extending it to be better at this, but it's still not perfect. And so oftentimes you have to kind of jump through hoops if you're going to use it in this context. Although I'm hoping having this project will motivate having more improvements to barb. Current fungible limitations. These are things that I would like to fix but aren't currently the way I'd like. Right now, defaulting is weird in terms of when you have things nested inside of record structures. There's no way to look at a bigger picture when you're defaulting. So like, for example, we don't want necessarily to default in the case where, we don't want to default the location information in the case where that piece of location information is matching. Sometimes we want to say if there's no information in location, and there's no location information, we want to default a certain value. If there's nothing there, then maybe you stick in that. But that's because in our software, it's designed so that sometimes you don't know which piece of location information belongs with another piece of location information. You just get fields from some database somewhere, and oftentimes they're all mixed up. So a lot of times these record structures, like that location one I showed you, will just have address. And then there'll be another one that just has the city, and there's another one that just has the state. And then I have code that essentially decomposes all that and then figures out things based on how much information is available. And it would be nice to be able to default at that level, but I have to do kind of a hack to make that happen. I'll show you that hack in a minute. The other big problem, as I see it, that would be nice for general use is just that it would be nice to be able to apply more functions to union types. It'd be nice to be able to replace union types easier. The biggest thing in the way of that right now is barb isn't really smart about union types. It's like C# level of understanding. So barb doesn't have pattern matching. It's not supposed to be a full-blown language, right? I made it for these little queries, and now things are getting kind of out of control. But it would be nice to have that. So yeah, and also because barb is dynamic, calling higher order functions where you have a lambda in barb and you're passing it into a .NET function doesn't really work out so well as things are, because it's really hard to figure out the types. Barb can deal with most generics just fine, but higher order functions in terms of like calling a .NET function with a barb function can be kind of, it doesn't work a lot of the time as of right now. Because there's just not a lot of, there wasn't ever really a lot of use case for that. Probably the best thing I could do to make that work is add some sort of type annotations to barb so that you can force types. But as things stand today, you can't do that. So, so here's the example of the hack that I was talking about. To be able to default a country, we have to make a function one, which is like kind of my escape hatch, like I said. And the function actually applies to the whole locations field. So here we just say, like, if none of the locations in the locations array have a country, we're just going to shove one in there with the default country. It's a pretty terrible hack, and I'd like to find a way to make it work nicer in terms of this framework. But essentially, the biggest downside is you can't just say default to this field with this value. You have to like call a special function in the library. So it's a little bit less nice because I have to have one of these for each of the location things. I'm kind of airing out my dirty laundry here with this. You know, like I want you to know that this framework isn't perfect. It really has been awesome for us. It's helped a ton, but there are some edge case stuff that I think requires some deep thought to be able to figure out how to do properly. So next I'm going to talk about some of the expression tree tricks. This is more of the advanced stuff. So I apologize, there's not going to be a lot of this. I've got 5 examples, but this is really like for the advanced F# users. So initially when I started building this, I was really struggling with the types, like trying to convert functions into the correct structure for calling inside of an expression tree. And Anton showed me this. Essentially, like I complained on Stack Overflow, and I was like, why isn't this working? And he's like, what you need is this pattern. Essentially, the pattern is made of 2 things. You have your get method function, which just unwraps and then makes a generic of the starting generic. It gets the generic type definition instead of having the generics filled in. And you also need this to be able to stick that in there. So this is actually this is an example of how it works when you have a map on an option type, right? This is just one little piece of code pulled out from the code base. So the way we have to do this is we put option.map in the quotation, only to get it out later. And we stick these x's in here. Now, this x of t, we're never going to get this unchecked default of value. It's purely a type placeholder, so it doesn't wreck the type. I know it's weird, but it actually works super nice. Without this, it's a nightmare. So essentially, you can just call this with these placeholder values for each of the things, like essentially, so it's not partially applied. You need to kind of apply it to the last thing that you might want to need, or you might want to need. You actually need. And then you just get method, which calls this, pulls the thing out. Because of these x's, the types will be correct. And then you just call .make generic method with the types that you care about. This is like the internal type of the option. Like, it's a container, it's got an internal type. And then we just call expr.call, which is saying is making a call, some function m, which is this thing right here. And then we're just passing it the updater and then the instance that we're going to be updating. And then we're recursing. There's a lot of recursion in this library. But this thing, if there's like one takeaway if you're going to deal with expressions in F#, like this pattern makes it easy. So much easier. Here's another thing I'm particularly proud of that took a little bit to figure out. How do you recursively build out these union types? Think about it for a second. There's like all of these cases, and you need to be able to handle each case. And I got that down pretty quickly. But then, because all you have with the expression trees is if and else, what do you do if you need a terminal case, even if you know it's guaranteed never to be called? Because F# is an expression-oriented language, there needs to be the right type in that place to make sure that things work out. So that's what this get typed exception is all about. I made this get typed exception. Essentially, it just does pretty much the same thing. But you can't just put a fail within a quotation and have it work right. It won't figure out the types after the fact. You have to make sure right now, when you make this exception throwing piece of code, it has to have exactly the right type. And here what we're doing is, essentially, this is all of the information you need to be able to build up the union type cases. So this is just F# reflection. We get all the cases out, they're case infos. We have a thing that generates it. I do this a lot because I think the expression API isn't very nice in F#. Like things are ordered badly, so you can't like leverage the partial application very nicely. So I actually wrap these things out a lot. Now we need a function for each one, or not for each one, for the one that we care about actually at the moment, based on the union case info, that actually will copy it. So this essentially is just a function that will copy through. For each field on the union case, we're just going to essentially generate a field copy, which is another recursion to a different part. I'll show you the code really quickly at the end. And then we need an expression that essentially makes a new union case. It takes the union case info to say which union case, and these are all the members, the new copied members. And then I just wrap up the expression that makes if then else. But with all these things, it gets like you can do this magic, right? Essentially, you can generate all the if statements and then fold over them, sticking them together, and then slamming the get type exception on the end. And I think it's great. I think this is just so beautiful, like the fold back, because it's just going chunk, 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 and making your nice nested if statements that copy all of the different potential cases for a union. I don't know. I think it's cool. Here's a very important thing to know. This is only in the newer versions of F#. I think as of 2012 it's in there. But there's this thing that converts. Now this doesn't work all the time too. This is important to know. Like it's a little bit fragile. It works all the time for what I use it for. But essentially there's this leaf expression converter type inside of Microsoft F# link runtime helpers that allows you to take an F# expression tree and turn it into like our standard .NET link expression tree. Because so like there is a project, an external project, that allows you to compile F# expressions. But I don't really like dependencies if I can help it. Instead, I'd much rather just have it be something that has a .compile already, which is the standard .NET expression tree stuff, which is used for link. So it's pretty easy. You just call it, cast it, get the arguments, and then wrap it in a lambda. Like the lambda body. It comes from this lambda here, which is just the first argument. So essentially, we're just wrapping another lambda to make it nice. And so that we can manipulate it later for that. I'll get to that probably if I have time. This is another really cool thing that actually is super helpful. It also makes it faster. Essentially, you can unnest all of the lambda expressions. So I go kind of crazy with my framework in terms of like using lots of lambdas to make it easy to knit all this stuff together. But then you can just call this little function, and it just takes away all the lambdas that are unnecessary, right? Like if you're just making a lambda for the sole purpose of jamming something into it in a moment, there's no point in actually having the allocation for the lambda. So I just pull out all the lambdas, and just nest all the calls appropriately. It's just like 6 lines of code. It's pretty simple, but it works quite nicely. And this is probably the most complicated one. So what I do to get that extra scope inside var is I leave a variable. I leave a variable that has nothing in it, and I call it replace me. And essentially that replace me is what will help be used for this make value container, which is that thing that has the scope and has the value. So the input arg is the thing that the tree will actually pass to it. But because for all of these functions, they only need one, like they can all share the same instance of the tree. Like you don't want to copy the tree if you're just passing it for inspection. And so by doing this, essentially we have this root type, and we can just replace, like later, take this root type and across all of our transforms, just swap in the replace me value, which is the tree. It took me a while to come up with this, but I wanted a nice way to be able to, it also, the other benefit of it is that if you don't use it, it's okay. Like it's just kind of like an extra value that's not doing anything inside the expression tree, essentially a variable definition. So it has the nice feature of not even being kind of exposed in the type signature necessarily unless you want it to, and you can just swap in that value.
So Rick, it's like you're instrumenting the code after you've compiled it? After you've...
Well, I leave like one final layer on the outside so that I can toss that value in there. And it's only used in the case where you're using var functions.
Right.
Although the value does exist in there when you're calling the static reflection ones. I just made it easier, like I didn't have to have all this branching for the different things. I don't think it really costs anything. But yes, here it's just, we're doing expert substitute with it, essentially just mapping over all the expressions. So finally, I just want to show you the structure of the core really quick. This is one of those cases where like functional programming is amazing because of recursion and co-recursion. You can do all this stuff. You can do everything with just like, this is literally like 2 pages of code at most. And it's just a bunch of co-recursive stuff. So I just want to give you a flavor of how it works. Just give me 1 sec. I need to switch this out. It's also on GitHub, so you can play with it yourself later. I think it's a pretty cool code base for learning about how to use F# experts, because it's pretty simple, and what it does is very straightforward, just copying stuff and injecting these transforms. But it leverages most of the techniques. Oh, okay, so we are in that mode. Were you seeing when I was talking about the slides? Was that like, did you see this before?
Yeah.
Okay, that's good. I was making sure, I was like, sometimes when I'm staring at this, it's easy to get out of sync. So here we go. I'm not gonna be using the REPL, so I'm just move this down. So the basic entry point is at the top. We just have this, essentially this is the dispatcher. It's the recursive function that calls all the other recursive functions. It just looks at the different types and calls the right one. Everything, when you get a new type, essentially it just goes, okay, you figure it out. Then for each one of these things, we have a function essentially for copying it or extending it. This is just a helper. It's not very important. This is just for like when you're passing one value to something versus when you have a tuple of values. It's not really that important. That's more having to do with the construction of the tree. So this is actually for copying tuples. Not that useful. It's just mostly saying like if we have a function, call it, and recurse generating the tuples. This is a get type exception. Record copier is interesting because you have to essentially recurse over each of the fields in the record. And we have to build out that string that we'll be using to look up in the map where we are so that we know what functions to apply. But overall, it's pretty simple. This is just for a field. Essentially, it's just like, it calls the thing above that just copies the expression, except it has a property get for the field. That's very simple. So here when we get to actually like when we're applying stuff. So this is just for a regular value. We're saying like if we have a map or a function, we just like apply it recursively. We work our way down that list that's on the right, that's in the value side of the map, just applying each of those. But you have to remember that it's not actually applying them. It's just building up the expressions that will apply them in the future. Slightly different. The code works out fairly similarly though. And all of these things, they return an expression. So like everything is returning expressions and it's just jamming them together. As you saw in the example before, we have this is for the option type. You notice that like collect and add, they throw because there's nothing you can't do those things to an option type. I guess technically, no, you can't, never mind. You could collect if the result was one thing, but that's the point. You might as well just map it. But it just used the same pattern over and over, essentially. We get our updater. This recurses getting each updater, then this batches on it, saying like, okay, this is the thing we're going to have to call for this updater. Make the generic method, make the expression call, and jam it in there, and then apply transforms, which is just a recursive callback up here. And then when we run out of transforms, we just return the instance. The instance is not the instance that we started with, it's the instance wrapped up in all these new expressions. And then this is the code down here that does the copying. The thing becomes extremely tiny if you're just copying and you're not worrying about applying these transforms. You just have a copy function, essentially to copy the internals, essentially add its map over them. That's like the standard operating procedure. I make a map function that just copies, essentially recursively. I know this is probably pretty confusing. I'm trying to just give you flavor. I think that if anyone here that's familiar with F# sat with it for like an afternoon, they'd really have a good idea of how it works. But just quickly, they also all have this pattern where, this is actually where this is what the first thing that's being called essentially is. And the dispatch is in these two other internal functions. First thing we have to know is if that there is in our map, if this path has anything associated with it. And the first two cases mean no. The second thing is do our settings say we should copy things anyway? If it's false, then we return the instance because we're not copying things. If it's true, then we copy it. Essentially passing in an empty map because we know there's nothing down this tree. That's more just for space savings and having to not look stuff up as much. And then finally, we might have transforms. Then this is actually the transforms themselves, because we're calling map.remove with that path saying okay, give us the path. Map.remove actually returns the thing that it removed. So that's extra, doesn't it? No, it doesn't, sorry. But then we just pass that through. Yeah, so we have our transforms. This is just the new funcs because anything downstream, you no longer, you don't want to accidentally copy. So this can actually happen because if you have for example, arrays of arrays or an option of array, none of the things have names in the middle, right? So where do you apply that? Now the answer is as deep as you can. But you need to remove the transforms once you apply them to make sure that they don't accidentally get applied in more than one place and explode, essentially. An array copier is quite similar. If you notice, you'll notice that these all have pretty much the same form. It's just the only difference is what things are in here, like the get methods, and pretty much, I actually was thinking that maybe it's possible to compress this code down a lot. It might make it harder to understand because they all have the same form. It literally is the same form over and over again. Map, it's the same thing again. Just for unions. Unions is the interesting one. It's got that kind of fancy fold back, jamming stuff together. And then our toLink function, where everything gets called. But this file is not that big. It's actually just seems big because we have our font really big. And then down here, there's the path generating stuff so that you can get that property map. And that's about all there is to it besides all of the extra stuff that actually does the wrapping of this. That's all quite fancy, or maybe fancy is the right word, not the right word. It's more gross in comparison, because that's where the metal, the rubber hits the road kind of thing. So I'll just finish up here. Oh, you're not going to make me go through them all again, are you? No, don't do that. Can I say from current slide? From current slide. That works. All right, so there's stuff on my blog. If you're new to F Sharp, I have a lot of blog posts about, a lot of them are older, but they're how I learned F Sharp and relating F Sharp ideas to C Sharp and things like that. I also write I've written a bunch about algorithms in general. A lot of my work has to do with algorithms, fancy algorithms for trying to figure out how to match names and whatever stuff like that. Combinatorics, things like that. You can email me anytime. I'm also pretty active on Twitter. I like Twitter. I'll respond to a Twitter message probably within an hour and an email within a week. So there's that. This is our user group website. You obviously know because you're here. And both of these two projects, Fungible and Barb, are on GitHub. Barb is in my own private GitHub because originally it was my own private project. But Bayard Rock, the company I work for, also has a GitHub account that we have our newer open source stuff on. Any questions? Was that understandable at all?
Yes.
That's good.
How does this whole thing compare to doing something equivalent in using XLC for an XML representation of the tree?
I've never really worked with that.
Oh.
I mean, the whole point with this is that we already have, when this stuff is being called, we already have all of these record formats built out. If they're not in XML, we have probably 10 different parsers for different formats that all go to the same structure. Now we want to be able to apply these data cleaning things across all of these different the inputs from any of these parsers or whatever. XML is one of the formats that we import, but if it would be hard to convert everything into XML and have it be nice, I think. We have a lot of weird data. Like things like maps are not particularly nice in XML. Like dictionaries. And also this is extremely efficient.
The part where you pass in the whole tree and then are able to pick out any point in the tree that's kind of reminiscent of what XPath does.
Yeah, that's
In
kind of what I
XML.
equated it to originally. Although it's not as flexible as XPath in that, you know, like with XPath you can say I want the second element,
Oh, yeah, yeah.
you know?
Yeah.
But there's no real point in having it be that flexible for at least what I use it for, because essentially we use it mostly for data cleaning. We want to apply the same functions across the board. The second element is sort of meaningless in that context, you know? But yeah, exactly, that's what inspired the syntax and the idea in the first place was I was like, wow, I want to do something like XPath so that I can have paths into my record structure in text, but from my settings file.
So how aggressively, when you get the AST of some of these guys, how aggressively do you try to like merge everything so it becomes like one efficient mutator?
Well, the most important thing that we do is remove all the lambdas. That takes away a lot of, because every function call is like not insignificant overhead in .NET. So removing all those lambdas saves a lot of effort. It's pretty efficient at it, mostly because it's such a simple idea. Like most everything that I'm doing is necessary and there's no smaller way to write it, you know? So there might be ways to speed it up slightly. As far as bottlenecks on our process go, this doesn't even show up in the profiler, like when this stuff runs. Compared to all of our features and machine learning stuff, it's like a drop in a bucket, I guess. Well, it's been great having you. I hope you have some cake. You know, there's plenty of Prosecco. We have like 4 bottles. Seems like nobody's drinking. We can hang out here for a while until, you know, like they're not going to kick us out anytime soon, I don't think. So
So let's get hammered.